Greetings! You are watching the fourth lecture on the course Introduction to Fourier Analysis. On the third lecture we managed to show that the complex exponential functions form an orthonormal basis in the space L2 of t. As a byproduct of the proof, we established the following uniqueness theorem for Fourier series. If f is a function in L1 of t and all of the Fourier coefficients of f vanish, then f is zero almost everywhere. The plan of this lecture is to cover a couple of easier results, some of which are based on the techniques which we use to prove the uniqueness theorem. In particular, we will recycle the fact that the Fourier kernels formed an approximate identity. However, the first result that we start with has nothing to do with the Fourier kernels. It is rather motivated by the Plancherel identity. This identity was recorded as a corollary of theorem 1.9. If f is a function in L2 of t, then its Fourier coefficients are L2 summable. More precisely, the sum of the absolute values of the Fourier coefficients squared equals the L2 norm of f squared. Now we are interested in the converse question. If an is any sequence of complex coefficients indexed by z to the power d, and the sum of the absolute values of the coefficients an squared is finite, then can we find a function f in L2 of t so that the an's are the Fourier coefficients of this function? Yes, we can, and this is the content of proposition 1.13. Let an be a sequence of complex numbers exactly as stated above, so the sum of the squares of the absolute values of the numbers an is finite. Then the infinite series of the functions an times en converges in L2 of t to a function f, and the Fourier coefficients of this function f agree with the numbers an. The proof idea of this proposition is simple. We consider partial sums of the form sum absolute value of n is less than big N an en, and show that these partial sums indexed by the number big N form a Cauchy sequence in L2 of t. Because the space L2 of t is complete, this Cauchy sequence will converge to a certain function which we will denote by f. At the end of the day, it will be easy to verify that the Fourier coefficients of this function f coincide with the numbers an. Let us then turn to the details. We should verify that the partial sums we mentioned before form a Cauchy sequence. To this end, fix two natural numbers big N and big N. Then consider the L2 norm squared of the difference of the partial sums with indices big N and big M. This quantity equals the L2 norm squared of the sum absolute value of n ranges between big M and big N, an en. To evaluate this quantity further, we recall that the L2 norm squared of any function is given by the L2 inner product of that function with itself. In particular, if we apply this formula to the sum of the functions an en, we arrive at the following expression. Once we expand the product of these two sums and exchange the order of integration and summation, we eventually arrive at the following expression. A double sum where both the absolute values of the indices m and n range between big M and big N of the terms average integral over t am times complex conjugate of an em times complex conjugate of en dx. Next, we split the double summation into those pairs of indices m and n, where first m is equal to n and second m is different from n. At this step, we also pull the constants am and complex conjugate of an outside the integrals. Now, in the first double sum, m is equal to n, so the double sum can be written as a single sum where the absolute value of the index n lies between m and n, and the product of an and the complex conjugate of an equals the absolute value squared of an. Also note here that the product of en with its own complex conjugate equals identically 1, and the average integral of the number 1 is also 1. To understand the second summation where m is different from n, we only need to recognize that the average integral of the product of the functions em and the complex conjugate of en equals the L2 inner product of the functions em and en. but since the functions en form an orthogonal sequence in L2 of t, such an inner product vanishes for all distinct indices m and n. It follows that the value of the second sum is equal to 0. So all that remains is the first sum, and we may finally estimate this sum from above by removing the upper bound big N from the index of summation. Looking back at what we have now accomplished, we have shown that the L2 norm squared of the difference of the partial sums with indices big M and big N is bounded from above by a tail sum over indices absolute value of n is larger than m of the coefficients absolute value of an squared. Now recall the main assumption of the proposition, namely that the numbers an are L2 summable. This means that the tail sum we just mentioned tends to 0 as big M tends to infinity. Hence we have shown that the partial sums of the functions an, en form a Cauchy sequence in L2 of t. Since L2 is a Hilbert space, this Cauchy sequence converges to a limit f in L2 of t. Note that this convergence is only guaranteed to occur in L2 of t, and we have, for example, shown nothing about the pointwise convergence of the partial sums a and en to the function f. However, the convergence in L2 of t is precisely what we claimed, and it is also strong enough to calculate the Fourier coefficients of the function f. Namely, the Fourier coefficient of the function f with index n equals the L2 inner product of f with the function en, and since the L2 inner product is continuous with respect to L2 convergence, this inner product is the limit of the inner product of the partial sums whose limit is f with the function en. Finally, one may use the linearity of the inner product to pull out the sum and the coefficients am, and in the end one notes once more that the inner product between the functions em and en vanishes except when m is equal to n. So all that remains of this sum is the coefficient an, and we have shown that the Fourier coefficient of f with index n equals an as claimed. This concludes the proof of proposition 1.13. We then move to a result which easily follows from the proof of theorem 1.9. Recall that this proof involved the Fourier kernels. These were the kernels defined as the average of the Dirichlet kernels, so the nth Fourier kernel fn equals 1 over n plus 1 sum m ranges from 0 to n ranges from minus m to m, en. We only define these kernels when the ambient dimension d is 1, and also the following discussion will be restricted to that case. The main point about the Fourier kernels was that they form an approximate identity. It followed that the convolutions of any LP function f with the Fourier kernels fn converges to f in LP as long as p is strictly less than infinity. If p is infinity, the same conclusion is not true as stated, but it holds if the assumption that f is in L infinity is upgraded to the assumption that f is a continuous function. During the last few lines of the proof of theorem 1.9, we derived the following explicit expression for the convolutions with the Fourier kernels. A function f convolved with the Fourier kernel fn equals 1 over n plus 1 sum m ranges from 0 to big N, little n ranges from minus m to m, f hat n en. Now observe that the right hand side of this equation represents a finite linear combination of the complex exponential functions. Because the function f is approximated by the convolutions f convolved with the Fourier kernels, we may conclude that in fact f can be approximated by finite linear combinations of the complex exponential functions. And this is exactly the main content of theorem 1.14. This theorem has two parts. The first one concerns LP functions and the second part continuous functions. In the LP part we fix an exponent p which is at least 1 and strictly less than infinity. Then, if f is a 2π periodic LP function on the real line, the linear combinations of complex exponentials defined just above converge to f in the LP norm. In the second part, f is a 2π periodic continuous function on the real line, and then exactly the same conclusion holds in the L infinity norm. The main point of this theorem is that f can be approximated by some finite linear combinations of the complex exponentials. What these linear combinations precisely are is typically not so important. For this reason, let us regard the main point of the theorem as a separate corollary. Finite linear combinations of the complex exponential functions are dense in the spaces of 2π periodic LP functions on the real line and also 2π periodic continuous functions on the real line. In the long run, it might get a bit tiresome to repeat all the time finite linear combinations of the complex exponentials, so very often these sort of functions are called complex trigonometric polynomials. Of course, if you take any one of these complex trigonometric polynomials and you really write it down explicitly, you will find that it's a finite linear combination of the functions cosine nx and sine of nx with complex coefficients. Let's make a few more remarks before concluding this lecture. The first one is that the type of summation associated with the Fourier kernels is often known as Cesaro summation. More precisely, a sequence of complex numbers an is said to Cesaro converge to a complex number big A if this kind of a limit of double sums which we have seen associated with the Fourier kernels equals A. It might be more descriptive terminology to say that the numbers an are Cesaro summable to the constant big A. The best way to look at this double sum is that it's an average of the standard partial sums of the numbers an. If you look at the double sum in this way, then it is not hard to check the following claim. If the standard partial sums of the numbers an converge to a limit, then the numbers an also Cesaro converge to the same limit. The converse is not true in general, so sometimes a Cesaro limit can exist even if the series of the numbers an does not converge in the standard sense. This discussion is relevant for us because in Theorem 1.14 we saw that if f is a 2π periodic LP function on the real line, then the sequence of functions f hat n times en Cesaro converge to f in the LP norm whenever the exponent p is at least 1 and strictly less than infinity. However, as we just said, Cesaro convergence does not in general imply the standard convergence of a series, so we may not immediately conclude from this result that the standard partial sums of the Fourier series would converge to f in the LP norm. It actually turns out that even this is true, but it requires deeper arguments. And of course, in the very special case when p is equal to 2, we have seen in Theorem 1.9 that the Fourier series converge to f in this standard sense. The reason why the case p is equal to 2 is so special is that L2 is a Hilbert space and the other spaces LP are not. So only in the case when p is equal to 2, lemma 1.8 is available to us. Recall that lemma 1.8 was the long list of characterizations for an orthonormal sequence in a Hilbert space to be an orthonormal basis. This characterization was really at the core of the proof of Theorem 1.9, and this lemma is not available for LP spaces when p is not equal to 2. This might be a good time to summarize the whole contents of these lecture notes. The partial sums of the Fourier series of a 2π periodic L2 function converge to that function in the standard sense. If the function is in LP and p is not equal to 2, then we have shown in Theorem 1.14 that the partial Fourier series of that function still converge in the LP norm, but only in the Cesaro sense. The convergence of the partial Fourier series also holds in the standard sense, but this requires more complicated arguments when p is not equal to 2. The reason for the differences between L2 and the other LP spaces is that L2 is a Hilbert space and the other LP spaces are not. I would like to finish the lecture with one more warning. In Corollary 1.15, we saw that the trigonometric polynomials are dense in the space of continuous 2π periodic functions on the real line. This result does not imply that trigonometric polynomials would be dense in the space of all continuous functions on the real line. In fact, this is clearly false. Every complex trigonometric polynomial that is a finite linear combination of the complex exponential functions is itself 2π periodic, and it is clearly not possible to approximate a non-2π periodic function in the L infinity norm by 2π periodic functions. In other words, no continuous function which is not 2π periodic can be approximated in the L-infinity norm by complex trigonometric polynomials. This concludes the fourth lecture on the course, Introduction to Fourier Analysis,